Hey students, welcome to the beginning of Unit 7. We're going to study some nuclear before we get into stars and astrophysics and cosmology. So getting started, how do we know about stars and other really distant objects? Have we traveled there? Have we taken a space probe and sampled it? No way, it's way too far. What we've done is astronomy. We've looked at light coming from those objects, and we can tell what they're made out of based on their emission spectrum, which is the very specific bands of light that come from electrons falling within specific elements. Each element creates its own pattern. And so by analyzing the light, you can tell exactly what's going on with that. Second thing we know is based on their blackbody radiation distribution, we can tell how hot the surface of the object is. So we can tell both what they're made of and their temperature by just looking at the stars or whatever other distant objects there are. Keep in mind, too, that if it's a colder object and it's not making visible light, you can still do this with infrared, microwave, or most often radio wave astronomy. So you can use a radio telescope and even look at very cold objects that are only emitting down in those frequencies. So this works across a pretty broad variety of stuff. One other thing, how do you know if the object is headed towards us or away from us? And the answer is it is the Doppler shift. Only we're not doing it at slow speeds with sound within our atmosphere. We're thinking about it at extremely high speeds, the kind of speeds you'd see between distant objects in distant galaxies, a fraction of the speed of light. And because of that, it's causing noticeable red shift if it's moving away from us, or blue shift if it's moving towards us, of those very same spectrum and frequencies. So we could see a pattern for hydrogen, and you could then notice the pattern for hydrogen, all of the lines in it are shifted just a smidge towards red. A little bit of math later, you could tell how fast it's traveling away from us. So the Doppler shift also tells us about the relative velocities towards or away from us. Not necessarily the right or left, but towards or away from. All right, so getting started. Let me see here. Got it. There we go. Okay. So we're going to do a little bit of nuclear chemistry today. I'm going to get you guys an introduction. We probably won't go into quite as much depth as we normally would since we're pressed for time, but we'll get you some essentials at least. You guys are going to know a bunch of cool vocab words by the end of this. All right, so getting started. You guys have probably already heard multiple times that in an atom, you have neutrons and protons in the nucleus, and then you have a cloud of electrons around the outside. Protons are positively charged, electrons are negatively charged, and neutrons have no charge at all. So that's kind of the essentials there. In the nucleus, those are the things that have a lot of mass to them. So protons and neutrons weigh a lot. Electrons don't by comparison. So when we're tracking the mass, the overall heft of the atom, we're tracking the protons and neutrons combined. Also, the number of protons then determines a bunch of stuff, like how hard it pulls on electrons, how many electrons it's able to capture, the ways those interact. So the number of protons defines which element it is, and is the most important thing you can look at, which is the atomic number. Atomic number is the number of protons. Now, the protons and electrons are often balanced out so that the positive and negative charge cancel, and the overall atom is neutral. But that doesn't have to be the case since electrons are pretty easily moved around, which is the main focus of this thing called chemistry. And so if you have a different number of electrons, you can have it be ionized. Ionized means charged up. Some atoms gain extra electrons, others ditch electrons and end up with a positive leftover charge because then it's the protons in the nucleus that are outnumbering the electrons in the electron cloud. Besides the fact that, let's say every atom with 6 protons is carbon, not all carbon atoms have the same numbers of neutrons. So an example would be carbon-14 has 2 extra neutrons compared to carbon-12. So the neutron count can change, but it's the proton count that determines the identity of the atom, which is why the atomic number is so important. And just one other thing, in a physical reaction, we're moving things around at a pretty big scale. In a chemical reaction, we're moving the electrons in the electron cloud. And in a nuclear reaction, we're actually changing the nucleus, hence the name. So that's kind of a quick distinction between those 3 things. Alrighty, before we get going with that, we are going to switch over to some paper and pencil practice here. This is Unit 7, Handout 1. If you guys are able to print it, that'd be sweet because it's got a periodic table on one side and some just simple practice on the other. And it looks like we're starting out looking at hydrogen. So we're going to go over here, find hydrogen. Whoop, there it is. Okay, it's got an atomic number of 1. That means it has 1 proton, and it has atomic mass of 1 as well. I know it's hard to see on your webcam there. Sorry about that, or my webcam. So 1 and 1 are the important pieces of information we need to take away from this. So headed back over. Symbol is H. The atomic number is 1. The atomic mass is 1. Here's what that means. Atomic number is the number of protons. These two things are the same exact idea. Atomic number is the proton count. So if this is 1, that's 1. Next idea. There is one total thing in the nucleus, of which one of them is a proton. Okay, so we've got one object in the nucleus, including 1 proton. How many left over are neutrons? Well, if we have one thing and it's already accounted for as a proton, it's definitely not a neutron. We have none of those. Last up, we're going to assume that these atoms are starting out neutral, meaning not charged up. And so if that's the case, the positive and negative charges will have balance. So if we have 1 plus 1 proton, we're also going to have 1 minus 1 electron. And there we go. That's the composition of hydrogen. All right, next one says helium. So I zoom over here. Here's helium. It has an atomic number of 2 and an atomic mass of 4. That's the information we need to pull off the periodic table. So zooming back over to helium. Symbol is He. The atomic number is 2. The atomic mass is 4. What does that tell us? It tells us that there are 2 protons because the atomic number is 2. Those two things are completely 100% identical. Then it's telling us that there are 4 total objects in the nucleus. Well, if 2 of those objects are already protons, then how many neutrons are we looking at? We need the protons and neutrons to add up to the correct total atomic mass. So 2 protons, 2 neutrons adds up to total atomic mass of 4. Last idea, we're assuming these atoms are neutral. That means that the electron count and proton count will be the same. So if we have 2 protons, we're also going to have 2 electrons, although electrons are subject to move around. All right, let's jump down to a harder one. K. K is potassium, right here. Potassium has an atomic number of 19, an atomic mass of 39. Okay, so atomic number of 19, an atomic mass of 39, and it is called potassium. Alrighty, so first up, how many protons does it have? Hopefully you've got this by now. Protons and atomic number mean exactly the same thing. That is the key defining feature of that element. Anything with 19 protons in it is potassium by definition. All right, how many neutrons is it going to have? Well, there are 39 total objects in the nucleus for a typical isotope. 19 of them are protons. That means the remainder, 20, must be neutrons. So basically, I'm subtracting this from this to get the remainder, which have to be neutrons. And last up, the electron count we're assuming is neutral. We're assuming that it's staying the same as the proton count for right now. When you guys take chemistry, you'll find out all the rules for how that's not necessarily always true, which is a good thing because atoms have to bond together and stuff. Alrighty, so I hope that this is super easy. You may know some of this already from prior grades like middle school science, whatever, but hopefully that's a quick review on how to decode the important information on a periodic table at kind of just the most basic surface level. I want to highlight too, we've got these abbreviations for proton, neutron, and electron. You'll see me use those abbreviations quite a bit. And with that, let's move back to other stuff. Okay, the other stuff is that we can write out a simple nuclear reaction. Don't worry, it's a lot easier than a chemical reaction. The balancing is super, super, super easy. So the way it works is, see those numbers across the top? I'm looking at the yellow, the first line of yellow stuff right now. I see uranium with a mass of 238. They're writing the atomic mass on top and the atomic number on the bottom of those two numbers, the superscript above it and the subscript below it. So uranium, it's telling me, has 92 protons, an atomic number of 92. And this particular uranium has an atomic mass of 238. So the way you'd say that is you'd say U-238 or uranium-238 to say which version of uranium it is. Some can have more neutrons, some can have less neutrons. So that number is subject to change. Anyway, that arrow counts as an equal sign. Okay, so we've got uranium-238 on the left. We've got thorium-234 plus helium-4 on the right. Now, what are you noticing about 238 equals 234 plus 4? Hopefully you're noticing that's true. Okay, so this is going to be really, really easy. The numbers across the top have to be equal on the two sides of the equations. Now check out the numbers on the bottom. What else do you notice? Remember, the arrow is an equal sign. 92 equals 90 plus 2. You can tell this is going to be really difficult, right? All right, let's look at the one below it. Does 131 equal 131 plus 0? Check. Yes, it does. Does 53 equal 54 minus 1? Yes, it does, and so forth and so forth. So we're going to be able to balance a nuclear reaction simply by making sure that all the masses add up before and after the reaction, and also that the total of charge adds up before and after the reaction. We're tracking mass across the top and charge across the bottom. That's pretty much it for now. We're going to switch back and do some simple examples. Don't worry about categorizing just yet. But now I'm grabbing Unit 7, Handout 2. Here we go. So, got this first equation. It says blank equals 14 plus 0. What equals 14 plus 0? Oh, 14 equals 14 plus 0. So I'm going to write 14 for the mass across the top as a superscript. Also on the bottom, blank equals 7 minus 1. Oh, that's going to be a 6, right? So the atomic number is 6, and the atomic mass is 14. Well, what has an atomic number of 6? I'm glad you asked. Right here, carbon has an atomic number of 6. So the identity of this atom is carbon. That first one, as far as just balancing it out, is done. That's really, truly, that's it. Okay, next one. 238 equals 234 plus, what would I need to add to 234 to get it to 230? Oh, 4. Okay, now the atomic masses are balanced. And across the bottom, I'm missing a 2. Now, what element has an atomic number of 2? I'm glad you asked. Here we go. Helium has an atomic number of 2. So the identity of this is helium. All right, moving right along. So 8 equals 7 plus 1. 15 equals 15 plus 0. Okay, now it's starting to get a little bit trickier. The fact that it's got an atomic mass of 0, or effectively close enough to 0 that we're going to call it 0, means that it's not a nucleon. It's not something that goes in the nucleus. It's not a proton. It's not a neutron, which leaves us with electrons. Now you might be thinking, well, that's weird. I thought electrons have a negative charge. You're absolutely correct. This is an anti-electron called a positron. It's an anti-electron. It's a type of antimatter. So that was weird. Sorry about that. So again, if you see an atomic mass of 0 across the top, it's not made of neutrons or protons. It's not an atom. It's some other particle, maybe like part of an atom, like an electron. All right, let's keep going. 15 equals blank minus 1. That's going to be 16. Also, 32 equals blank plus 0. That's going to be 32. Am I looking up 32 or 16 on the periodic table? Which one? 32 or 16? I'm looking up the atomic number, 16, and that tells me this is sulfur. So right, big capital S right there. All right, cool. Hopefully you can keep going with this. The ones on the bottom, I wrote out in more word problem-y form. They're a little bit more challenging. Let's try one of these. The element californium was first synthesized by bombardment. An element, okay, that's our mystery, was bombarded with an alpha. Oh, well, yeah, we're going to have to come back to this in just a sec. Okay, let's switch back to our slide here. All right, there's effectively about 4 or 5 categories of stuff you need to know about. So you're going to need to be able to identify radiation particles, not like of the electromagnetic variety, but actually of chunks of atoms flying off. And the first one's called an alpha particle. It's effectively helium. So if you see helium, If you see helium, call it an alpha particle in most cases. If you see an electron, call it a beta particle. If you see just a pure chunk of energy, call it a gamma particle. In this case, that is a photon. That's the radiation way we thought about it last unit. You can also have a positron, which is an anti-electron. I'm okay with you guys calling this beta, but it's probably better to distinguish between positrons and a regular beta particle like that. We're also going to look for lone neutrons, and we're going to list those out. So you guys are on the hook for identifying helium, for identifying electrons and positrons and calling them beta decay or beta whatever. Also for gamma, which is just energy, and last up for neutrons. Okay? So there's basically only a couple things to keep track of here. I'm going to list those. Actually, let's go just dive in right here. Do we see in this one any of those things we just mentioned? Well, there it is. What is that? That is a beta. Electrons go with beta. Now, is it going in? Is it an input to the thing called a reactant? Or is it coming out called a product? Reactants on the left, products on the right of the arrow. What goes in, what comes out. That's the way we read a chemical reaction. Well, this is going to be coming out, so I'm going to use the word decay. Decay is a good word for it's coming out. Okay, number 2. Do we see anything that we just talked about as a kind of radiation particle? Yes, we do. Helium, the name for that was alpha. Is it a reactant or product? It's on the outbound side of the arrow. It's a product, so we're going to list that out as a decay again. Okay, this one we already identified as a positron, and it's coming out, so we can say decay again. This one here is an electron that's categorized as beta. Cool. Let's try this next one. 47 plus blank equals 46 minus 1. 105 plus blank equals 105. 0. That's not an element. That's not got anything in a nucleus that's got substantive mass. What that is an electron. No significant mass, -1 charge. Okay, that is a beta, right? Is it on the inbound or outbound side? That is a reactant. That's inbound. So instead of using the word decay, I'm going to use the word capture or bombardment. Those are both fine. Alrighty, so let's keep going. Now let's try one of the harder ones. So an element was bombarded with an alpha particle. We need to know that an alpha particle is a helium atom. So we have an element, we don't know what that is yet, and it's bombarded by an alpha particle. So I go look up helium, and I find out that it's got an atomic number of 2 and atomic mass of 4. And now it's telling me the products, so it's a good time to put my arrow. The products were californium 245. 245 is the mass. I'm writing that up at the top. And I'm going to go on my periodic table and I'm going to find that weird thing called californium. Where is it? Oh, right here. It has an atomic number of 98. So I'm going to put 98 down at the bottom here. And then it's also saying and a neutron. So and a neutron, I'm going to use the symbol N. It does have mass. It's one of the things that makes the nucleus heavy, but it does not have charge. Okay, now we can back solve whatever this thing is. So 98 plus 0 equals blank plus 2. That's got to be 96. And over here we've got 246. Take away 4 is 242. And I'm going to check on my periodic table. 96 is curium. It gets the symbol Cm. Alrighty. Now, what counts as radiation particles in this one? The helium and the neutron. So we've got helium we got alpha capture or alpha bombardment. Either one is fine. It's on the input. We've also got neutron decay or neutron emission. So you could use the words, if it's coming out, you can use the words decay or emission. If it's going in, you can use the words capture or bombardment. Don't worry too much about which is which right now. We're doing this on easy mode. It's all good. All right, let's try one more. We've got hydrogen 2. Okay, periodic table says hydrogen has an atomic number of 1. So I'm putting 1 on the bottom. What's that 2 for then? Oh, that's the mass. Okay, that goes up top. And then we've also got hydrogen 3. Looks like that. And they're combining. So, okay, so now this is afterwards. I put my arrow to make helium 4 and a neutron. A neutron has no charge, but it does have mass. And we'll double check. 5 equals 5. 2 equals 2. Yep, this works. All right. Now, weird story. This is actually called deuterium, and this is called tritium. They're isotopes of hydrogen. They have unusual masses. These are basically chemically just like hydrogen is, but they're heavier. And if you made water out of them, you'd have what's called heavy water. And actually, one of the most famous raids in World War II was to go blow up a pool of heavy water that Nazis were using for their weapons research. It set back their equivalent of the Manhattan Project a long time. You guys can go on YouTube and read about it or watch a video on it or Wikipedia or whatever. It's pretty cool. And my dad actually, he works on a fusion reactor using this exact reaction right here. So my dad actually works on this exact process. They can use some lighter elements, some lighter isotopes of hydrogen as well. But if they add deuterium or tritium, it makes the reaction a whole lot more powerful. Oh, this is the thing in Iron Man. You know, the big arc reactor? That's this reaction. This is also a reaction that happens in stars, which is one of the reasons we're learning this. We're going to talk about this later. What you'll notice is 2 small atoms, in this case hydrogen, turn into a bigger atom, helium. And so this also gets the special category name of fusion. Fusion is when 2 small atoms get combined into 1 bigger atom. Alrighty. On the back of this, there is a decay chain. I'll get you guys started on this. Uranium-235, and I have to look up uranium, and it says 92 for its atomic number. It emits, so now I put my arrow, and it emits an alpha particle. We know the identity of an alpha particle is a helium atom. Hopefully you're starting to get used to just knowing that one. That's a quickie. And what that leaves is 90 on the bottom and 231 on the top. And on my periodic table, I go check out 90, and it's thorium, which is my favorite heavy element, my favorite radioactive material, basically. You used to be able to get a bunch of thorium on the old Coleman lantern hoods. Like, you guys know the thing where you got the little torch inside the camping thing and it makes a ton of light, it's super bright? Those used to have thorium in them. They don't anymore. But if you got the old ones, you could get a whole bunch of thorium and you could get your Geiger counter and it was totally radioactive. Good stuff. And there's this weird saying, I don't know where it even came from. I think it was some physics conference, don't drop the thorium. We were passing it around at a conference and somebody's like, don't drop the thorium. We all thought that was hilarious. We were very careful not to drop it, by the way. Yeah, so don't drop the thorium. That's my favorite element. Now, here's the point of this. This is a decay series, a decay chain. Uranium was radioactive, and it broke apart into smaller atoms. When a big giant one breaks apart, by the way, it's also called fission. Not just alpha decay, but also fission, another category. Now, the problem is that the thorium is also radioactive. Good reason not to drop it. So what we're going to do is we're going to start the next one with the thorium. And then this one emits a beta and a gamma. So I'm going to write a beta, that's my electron. It has a negative charge but no significant mass. We're also going to put in a gamma, which gets that weird Greek Y symbol. That one is just a burst of energy. It doesn't have any mass or charge associated with it. You don't need any numbers for that. Just show that some energy came out. And you guys know that's the most energetic frequency of light, too. It's way past ultraviolet and X-ray. And last up, 90 equals blank minus 1, 91. 231 equals 0 plus blank, 231. So now we'll check real quick, and 91 and 231 gets me protactinium, whatever that is. And lo and behold, protactinium, we're going to start out the next one with protactinium. So this is a decay chain. You keep using whatever your product is to start the next thing in the series. Now, for review, let's go down here and let's just define alpha. Alpha is helium. Beta is an electron. Or you could have a positron. Gamma is just light. We don't need to worry about any numbers or anything like that. And the last one, a neutron, we would write it with mass, but not with charge. Okay, last idea. Radiation is a confusing word. Radiation could mean electromagnetic spectrum. Okay, so radiation could mean radio, you guys should know this, microwave, infrared, visible, ultraviolet, X-ray, and gamma, of which ones that can ionize atoms, move their electrons around, have enough energy to lift electrons off, these ones can be hazardous because energy is proportional to frequency. Higher frequencies carry more energy, have enough energy to cause damage to DNA, cells, etc. The other thing, though, we're also talking about these chunks flying off atoms as potentially hazardous. So gamma radiation belongs to the electromagnetic spectrum, but the rest of these are chunks that fly off atoms. They have actual mass. They fly at less than the speed of light. They're fairly easily stopped. So a lot of times you can shield against these pretty easily. One thing that's weird, though, is if they stick to something, they can change it into a radioactive isotope, and they can trigger a decay series. So sometimes, like, getting hit with a neutron is bad, not because it does damage right away, but because it'll change the element and then cause a decay series that can cause later damage. So there's still hazards with these, but you can shield most of these even with just a piece of paper. So just, try not to eat these things that make these radiative particles. But on their own, they're probably not too bad. Okay, so that's that. I think that's both handouts. I'll have keys up for you later. Let's keep going. So one idea is that charge is conserved. Those are numbers across the bottom. Another idea is that mass is conserved. If we're rounding the whole numbers, that's true. But what's weird is, if we are looking at like very, very fine details, that's not entirely true. A tiny, tiny bit of mass disappears and is converted to energy. So the whole point of a nuclear reaction is that mass can convert to energy, or vice versa. Energy can convert to mass. Now, c is the speed of light. That number is 3 times 10 to the 8th meters per second, which if you square it, it was already a big number, but squared, that's a crazy big number, right? 9 times 10 to the 16. So what that tells you is even a tiny, tiny bit of mass, if it disappears in the process of a chemical reaction, a nuclear reaction, I misspoke, can liberate a whole lot of energy. By the way, this is also true of physical and chemical reactions, but the differences are so small and subtle, they're basically almost impossible to measure, and we don't even worry about it. So for physical and chemical reactions, mass is truly a conserved property. For nuclear reactions, we are close enough that if we're rounding the whole numbers, you'll never notice. But we know that there is mass-energy conversion going on. So you have to think about both energy and mass when you say it's conserved as kind of a combined total. And so, by the way, here's some cool images of, I think, one of the nuclear weapons tests. I think that's Bikini Atoll. Actually, I think one of my relatives was the pilot for that drop. I forget. Um, anyway, point is that a tiny bit of mass vanished in the process of that bomb going off, and it converted to a whole lot of energy in the process. Now, why is this a good thing? Well, the good thing is what you're looking at is a fission reaction predominantly, like uranium or plutonium slightly disappearing as it breaks apart. But what stars are doing is fusion. We mentioned this earlier. Hydrogen plus hydrogen can be turned into helium, it can be fused. And this also has a little bit of mass go missing. And this energy conversion is the thing that's powering stars, which is super important because, of course, that's powering everything else. So fusion reactions make the universe go round. That's like where all of our energy comes from at a fundamental level is fusion. And how much is it? Well, those four things on the left, those are all chemical reactions, all excellent fuel sources. And on the right, we have a fission reaction, a big heavy element like uranium breaking apart. And if you wanted to print the graph of it, that's how much energy it would take. It would take stacks and stacks of paper just to get the idea through of how much energy is in there in a nuclear reaction when the mass actually converts to energy. So pretty cool. This is also roughly equivalent to the thing that's powering stars, which is fusion reactions, typically based off hydrogen. We'll talk about more when it's not later. Now, hopefully that was all super easy to digest and fun and happy. Next thing, protons and neutrons are not the end of the story. There's actually smaller pieces that go into building up a proton or neutron. They've got some pretty weird names. Protons and neutrons are made of quarks. A proton is made of up, up, down, and a neutron is made of up, down, down. Basically, both protons and neutrons are made up of quarks in sets of 3. And I don't know if you guys can see on the up quark, there's the charge of 2/3. That's the charge right here. 2/3 plus 2/3 gets you up to 4/3. Minus 1/3 gets you to 3/3. That's just 1. That's why a proton has a +1 charge. It has 2 of these and 1 of those. Or if you had a neutron, you'd have 2/3 minus 1/3 minus 1/3 would get you down to a charge of 0. So that's why a neutron is up, down, down. They're both about the same mass. So they're both kind of equivalent as far as the weight or heft it's giving the nucleus. You can, it turns out, build super weird types of neutrons and protons that are much, much, much heavier than normal and are unstable and decay on their own out of the neighbors of up and down, which include charm and top or strange and bottom. They give them some pretty whimsical names, by the way. But basically, any combination of 3 of these things called quarks can make up a nucleon, something that gets stuck in the nucleus. And you'll notice that down there at the bottom, there's electrons. Those are a completely different category. The good news is, as far as we know so far, an electron is made of an electron. So I hope that's a relief. But a proton and a neutron are not fundamental particles. They're made of smaller pieces that you may not have heard of before. By the way, an electron also has heavier, more unstable versions of it called a muon or a tau. So I want you guys to think of these columns as tiers or generations. And the one on the left is the stable, basic, everyday version. The one in the middle and the right of these 3 columns is heavier, rarer because it's unstable and they tend to decay back into the simpler form. Let's see. The items in red, those are force mediators. Those are particles that zip back and forth and they carry force. So a photon carries electromagnetic force. A gluon carries the strong nuclear force. And the Z and W bosons carry the weak nuclear force. We've talked about the 4 forces before. And a lot of scientists think that there should be a graviton, something that carries gravity and is a force mediator for that. But we have not verified that experimentally yet. We cannot prove that there's a graviton, except for the fact that there is gravity. We haven't isolated the particle, though, so it's not yet on this list. Also, the property of mass may be mediated by the Higgs boson. So mass and inertia may come from this guy over here. So this is called the standard particle model. There's a ton of experimental evidence behind this, as well as some good modeling. Some of these were predicted to exist before they were actually found. The way they find them is often in a super collider type experiment, which you can Google. CERN, CERN, is a great search term to pop on YouTube, and I'll link a video as well. And we're talking about this because we think that atoms are normal based on everyday life today, like you look around, you see stuff made out of atoms. And that's when we get these quarks in sets of three trapped in a nucleus with an electron orbiting around the outside. That has not always been the case. There are different ways to arrange these two. You can get quarks set up in sets of two. That would be normal under really high pressure, high temperature situations, like exceedingly hot, dense scenarios. You'd actually get your quarks in sets of two. You'd also, before things had time to decay and at higher energy levels, you'd get more stability on the second and third tier when you've got all these crazy heavy things than you do today when things are cooled off and settled down in this first tier. So keep in mind that the way we have things today with regular old atoms isn't necessarily the only way you can arrange these particles. There are many other ways to arrange these particles, notably quarks in sets of two, or even individual lone quarks called quark soup, which we'll talk about later. So that's kind of probably the weirdest thing you've heard about. Here's some cool diagrams. This explains how and why. Well, this is kind of a mental model we have. Obviously, these things don't actually have a color. So it's not like there's a red quark and it looks red. These are just names. You know how like positive and negative are just words for two things that could be opposite? Or like north and south? What does it really mean? It's just the names we put on stuff. Anyway, they thought that using colors would help explain different possible combinations. Any quark bonding arrangement which results in white counts. So you could have red and anti-red, or you could have red, green, blue. And both of those would result in a white chromodynamic charge arrangement, which is why you can get quarks in sets of three or two according to this model. Well, that's not really explaining why, it's explaining what. That's what's happening. We're also looking at different ways that particles can change and decay. And so this is called a Feynman diagram. If we have time, we'll go through this a bit later. It's pretty cool. But what you can tell is there's a neutron based on up, down, down, converting into a proton based on up, down, up. And so a neutron can convert into a proton. In the process, it gets mediated by a boson, and electrons pop in, and an anti-electron going back in time pops out. Sorry, electron neutrino. It's pretty weird. All kinds of stuff happens. The model that we just used on our handouts, you just call this a beta decay. You notice there's an electron popping out, beta decay. But what's really happening is the charge, momentum, mass, and energy are all conserved and transmitted by this force-meeting particle, the W boson in the middle. And in the process, one of the quarks flips from down to up, meaning that the neutron converts into a proton. So that's actually kind of what's happening at a more detailed level than you guys need to know, but I want you to be at least aware of this. And this is a chart that says what affects what. So like Higgs boson provides mass and inertia, and you can tell which particles don't have mass or inertia, which include the photon, right? Or like photons deal with electromagnetism, and we associate that with the property of charge. So you can see which particles have charge. And that's our leptons and some of our bosons here. So there's a whole bunch of kind of interactions that are pretty cool to map out. And that should do it. So you guys got an introduction to the idea that nuclear reactions is where something in the nucleus is changing. We can pretty easily map that out by tracking charge, including using atomic numbers, and also by tracking mass, including using the atomic mass. That there's a couple pretty common patterns that we count as radiation particles, like alpha, beta, gamma, and neutron. And that one of these reactions, called fusion, is where small atoms combine into a bigger one, and this is what's powering the stars. The energy is coming from the mass defect, the missing mass that disappears and converts over to energy while this happens, which is pretty subtle but noticeable in a nuclear reaction. It's not noticeable in chemical or physical reactions. And last up, that there's a level of detail that you may not have heard of before, called the standard particle model, that sits below the electrons and protons and neutrons that you probably have heard about. So there are some more smaller subatomic particles than just protons and neutrons in the nucleus. And I'm just putting the idea out there right now that sets of three quarks is not the only stable arrangement for them. They can also exist in sets of two or under like super crazy conditions, even individually. And we're going to talk about that later when we get into cosmology. So that's that. Stop by office hours if you need anything, and I'll talk to you guys soon. Bye.